I think waves is a relatively simple chapter, but it actually sets the context for subsequent chapters like EM wave, your light, and also on sound. So that's why for waves, right? This is really a good introduction into what waves are. And once you're able to understand this better, you'll also be able to answer the subsequent questions better from the other chapters. So let's start now. Let's do blue color for today. So waves. Okay. Now, so 11.1 waves. So first thing, in this 11.1, they will actually be showing you how to describe wave. Okay, because it's really an introduction. So in case people are not so sure of waves, they are actually going to give you many examples here. Second thing they're going to pick up is that waves actually transfer energy without the transfer of the matter itself. So waves transfers energy, okay, without the matter being transferred. And the next one, we're going to look at the difference and similarities between a transverse wave and a longitudinal wave. So differences and similarities. So these are the three that we'll be covering for 11.1. Okay, so now let's start off simple things first. What is a wave? So a wave is made up of a periodic motion. Where the word periodic actually tells you it's a repeated motion. A repeated motion. So taking a pendulum, you can see whenever you let the pendulum swing, it goes left to right, right to left. Right? This is a periodic motion. So actually, this is made up of a wave. But this is a wave in a sense. Okay, now I need to take note. One complete cycle of such a motion is known as the oscillation. So what does it mean for it to be a complete cycle? So when we say it's a complete cycle, means first thing, okay, it needs to return back to its original position. Right. Second thing, if it is a complete cycle, the motion is repeatable. Okay. When I say the word repeatable, it means if I were to look at it, I can let it go on and on and on. It will show you the subsequent motions also. So for example, in this case here, if I start off at A, for it to be considered an oscillation, it needs to go towards B and then come back. This is to fulfill the first condition of it returning to the original position. How about number two? Okay, number two, we talk about, the motion must be repeatable. So can you see going there, coming back? If I repeat it, going there, coming back, you see the motion is repeatable. Okay, some people's common mistake is that they say cha. Okay, A to B itself is a complete motion. It's a complete motion. Right? This is known as an oscillation. So the red color here, wrong. It is not an oscillation. Okay, because what do I mean by it's not repeatable? You see, when the ball goes from A to B, can I repeat this motion again? The ball is at B now. How do I get it back to go from when it's at B? How do you get it to go from A to B, A to B, A to B, A to B, A to B? You realize that it's impossible because once the ball reaches B, it is over here now. How do I keep repeating this going towards the right motion? It doesn't work out. That's why the motion, when I say it's repeatable, means that you must be able to let it run on its own. Okay, it doesn't give you like those kind of stop, come back to original position, stop, come back to original position, that kind of setting. Okay, so when we say it is repeatable, it needs to return original position, so it will actually be going from A to B and then from B coming back to A. Okay, so a wave is a periodic motion. One complete cycle of such a periodic motion is known as what we call an oscillation. Okay, so that's the first thing. Now, I want you to take note of this part over here. The source of any wave. Okay, so for you to produce a wave, what do you need? You need a vibration or an oscillation. So this is an oscillation, that's why you can produce a wave. A vibration, okay, I think most of you would have also know what a vibration is. So take note, the source of any wave is a vibration or an oscillation. Right? That's one property of a wave. Another property of a wave is that a wave is there's a disturbance. Okay, it actually transfers energy from one place to another. Right? This is the second property. So source is one. The wave transfers from energy from one place to another. That's another one. The next one is it does not. Let me use a different color. I'm sorry, missing color. It does not transfer matter during the energy transfer. So the matter itself is not being transferred, okay, in the midst of the energy transfer. Point 1, 2, 3, we're going to look a little bit more in details in the subsequent examples. Okay, so now let's look at this. So let's look at waves. So this example here will go very lengthy, but it actually gives you quite a good way to explain. It gives you a good understanding. The explanation gives you quite a good understanding of what the book is trying to explain. So let's look at it. So initially, when you pull a rope straight, okay, this is the fixed end. This is the hand that holding the rope, right? So in order for you to produce a wave, your hand will move up and down, up and down, up and down. So as it's moving up and down, what's happening is that the KE, this is the energy, okay, is being transferred. So this is the concept of energy being transferred from one place to another. So when my hand moves up and down, the wave actually the rope, okay, the rope actually using a wave carries the energy from the hand all the way to the wall. So the KE from the moving hand is transferred to the rope by the rope wave. The rope particles near the free end moves up and down as the wave passes through them. So you can see here, P goes up. Then after that, as it goes up, it will come back down. Q on the other end will go up and come back down. So the motion at each point of the rope is also going up and down as my waves travel from left to right. So look carefully. The wave is going from left to right, but the particles, my hand, okay, the PQ particles, my hand is actually only moving up and down. It is an interesting concept of the rope wave that we are seeing here. Okay, this is actually known as the transverse wave, which we will go into it later on. Now, so the K of the rope particles near the source is transferred to the rope particles further away, example Q, as it progresses. So the energy is being transferred slowly along the rope, okay, and the rope wave continue to move towards the wall until it reaches the wall. So you can see at this point here, the rope itself, the whole rope did not move forward. I say again, the whole rope did not move forward. Instead, it seems like as though the rope is moving forward, but it's not. The rope is only moving up and down along this part over here. Okay, so what can we say about this whole example? First thing, you actually can say that the source is an oscillation. Okay, the source is an oscillation, which is the hand moving up and down. Secondly, we can see that the energy is transferred from one place to another. Next thing, okay, which is the last point over here. So you can see here, the last point which I underline, right? It does not transfer matter. Okay, so the rope is not transferred. Okay, the rope is not transferred, okay, from one point to another, from the start point to the end. Okay, so this is really just to showcase the understanding of what a wave is and the property of a wave. Right? These are further examples that you can take a look. I will not be going through them. Right? That's why I mentioned that the textbook is actually very comprehensive. But most people don't like to use the textbook because too much info. What do I need to know? What do I not need to know? Right? So that's why I'm purposely going through the textbook, so you know how to filter through it. Okay? So this one is just a further example. You can read out on it, but you realize it's exactly the same thing. Okay? So for this case here, the deeper is the source. Okay, then they're gonna explain to you, what it means by the energy is transferred from one place to another. What does it mean that the matter is not being transferred? Okay, and stuff like this. So you can read up. Okay, it's quite a good read. Next, wave in a spring. So Slinky, I think this is a common example that the teachers like to bring to the classroom to show you. So what we have here is a Slinky. Okay, there's two different type of ways you can make the Slinky move. One is making your hands go in this direction. The other one is go by a push and pull here. These two are considered waves, but they are different waves. Okay, so the Slinky is able to produce these two type of different waves. This type of wave is known as what we call a transverse wave, whereas this part here, this wave here, is known as a longitudinal wave. So we're going to go more in details about this transverse wave and longitudinal wave in our next part. But as a wrap up for this segment here, these 3 points is what we wanted to cover. Okay, these 3 points over here was what I wanted to cover, which I did mention at the start. Okay, when we talk about the properties of the wave. So by now, by the end of this part over here, you should know that the source of a wave is a vibration or an oscillation. Waves actually transfer energy, and waves transfer energy without transferring the medium. Okay, the medium could be the Slinky, could be the rope, could be the water itself. Okay, so that's what they mean by transferring energy without the transfer of the medium. This is the one where most people struggle with, so my suggestion, go and read out on examples a little bit more and wrap your head around it. Okay, next. Now, types of wave motion in your syllabus, there's transverse wave and longitudinal wave. So how does a transverse wave look? Typically, okay, let's look at this example here. Okay, what you are seeing here is that the hand is going up, going down. So hand is going up and down, whereas the wave is moving from the left to the right. So look at this whole thing here, look at the motion. The wave is consistently going to the right, but the wave, okay, but then the vibration, okay, the particles are actually moving up and down. So you can see here up and down, etc. So why do we call this a transverse wave? So do take note, the idea of why is this a transverse wave, because the wave travel is perpendicular to the vibration, direction of the vibration. So in this case, the wave is going towards the right, the vibration is up and down. So can you see the perpendicular? 90 degrees. So transverse wave is very unique in a sense that the waves actually travel, okay, the wave actually travels perpendicular to the direction of the vibration. So the particles moving up and down is actually known as the vibration. So do take note of this. Okay. So this is a transverse wave. Now we're going to go on to a longitudinal wave. I like to highlight this part over here. Okay. I don't know whether it's a good or a bad thing, but in your syllabus, okay, the only longitudinal wave is sound. Okay, the only longitudinal wave is sound. So as long as they ask you an example for longitudinal wave, or they ask you which is not a longitudinal wave, only just remember longitudinal wave equals sound. Then from there you answer all the subsequent questions. Okay, so I just want to highlight this point here. But now let's look at the wave motion. Okay, so the wave in this case here, as you look at it, right, the wave is going in this direction, going forward from left to right. Okay, this is the wave direction. What is happening? The hand is pushing forward, going backwards, going forward, going backwards. Okay, so you can see the hand is moving forward, backwards, whereas the wave is going towards the right. So this is the vibration or the oscillation. Now, what do you realize about this compared to the previous example? So this is the vibration. This is the direction of the wave travel. This is the wave travel direction. This is the vibration direction. Okay, this is the vibration oscillation direction. This is the wave direction. What you realize is just now previous one in the transverse wave, it is perpendicular. But in this case here, you realize it's not perpendicular. Instead, the keyword used here is parallel. Okay, these two lines here are parallel. So the direction of the vibration is parallel to the direction of the wave travel. So transverse wave, you will see that very unique 90 degrees. Whereas for longitudinal wave, you will see that both lines are parallel to one another in terms of the vibration direction and the wave travel. So if you look at it, this is the definition for longitudinal wave. There are waves that travel parallel to the direction of vibration. So wave travel, okay, I'm just going to summarize the part here. Okay, compared to the vibration direction, vibration direction. Okay, pardon my handwriting. Okay, now if the wave travel and the vibration direction, they are perpendicular to one another, then we say this is a transverse wave. So realize I'm trying to show you that the wave travel and direction of vibration is consistent. It is just really whether is it a perpendicular or whether it is a parallel. So if it is parallel, then we will term it as a longitudinal wave. Okay. So do take note of the difference between a transverse wave and a longitudinal wave. And I mentioned longitudinal wave, the only one in your syllabus that you learn is sound. Okay, so this will help you quite a fair bit here. So just to wrap up for this segment of 11.1. So periodic motion is a motion that repeats at regular interval. Okay, one complete cycle is known as an oscillation or vibration. Okay, so done. We mentioned about wave transfer energy from one point to another without transferring the medium. That's another one we've covered. This is under the property of a wave. There are two types of waves that we see, that we have learnt. One is called the transverse wave, one is called the longitudinal wave. A, B. Right, we covered this. And the last one, last two. Right, we learned about transverse wave and its definition. So the keyword here, perpendicular. Longitudinal wave, we also picked up parallel. And as I mentioned, sound wave is the only one that's quite unique. And do remember that this is the only longitudinal wave. This pushing and pulling of a slinky, I don't really see it come out in the questions. Okay, but of course, the push and pull, the example is given, so I think it should register in your mind quite easily also. Okay, so this is for 11.1. Now, let's go on to 11.2. So we're going to really look at the wave motion, the property of the wave motion. So we're going to pick up in this now 11.2 is that we're going to, with reference to waves, we're going to learn about the concept of the speed of the wave, frequency of the wave, wavelength, period, amplitude, and wavefront. So 6 different terms, okay, for you to pick up in terms of describing a wave. And actually there are still some more. The other one is you're going to learn how to apply this formula here, which is V, which is the velocity, equals to frequency, F, times the wavelength, which we call lambda. Later on we'll go into it. So this is the formula that you realize in your exams, it keeps coming out. You need to get familiar with it. Okay, so let's jump into the segment itself now. So describing a waves. So look at this whole rope here. Okay, I'll go through term by term now. First one, in this whole rope thingy, the first thing that's being highlighted is the amplitude. So the amplitude of a wave is the maximum displacement. So the maximum displacement means the maximum change in position. Okay, it's the maximum change in position of a point from its rest position. Now, so in this whole thing here, first thing you need to know, where is the rest position? So this thing in pink is the rest position. So if the rope is not being moved up and down, actually the rope will just be along this straight line over here, and that's what we call the rest position. Okay, amplitude is the maximum change in position. So if originally is here, can you realize that this point will be the maximum? So maybe I should use a different color. So from here all the way up here, this is the maximum change in terms of the position from its rest position. Okay, so that's why this is called the amplitude. Now, this is also called the amplitude because going all the way up or going all the way down, this two length is normally the same. Okay, so that's why these two are called the amplitude, because both the height is the same. That's one. Second thing is it also shows you the maximum displacement. Do take note, because it's a distance, amplitude is a distance that's being measured. So the SI unit is meters. Okay, so this one is what I've gone through just now. So this is amplitude. Next, this is the concept of in phase. Okay, in phase. Now, what do they mean by the points are in phase? So they actually gave 3 examples of what they mean by points are in phase. Okay, but in definition, they are points that have the same direction of motion, same speed, same displacement from their rest position. Now, how do you know all this? Okay, it's not going to be easy. Therefore, the textbook actually gave you examples. All the crests are in phase. All the crests. So here, here, here. These 3 points, because they're all crests, this is in phase with this, this is in phase with this. Another one, let's use a different color now. Okay, all troughs are also in phase. So troughs over here, troughs over here. So these 2 points are also in phase. Now, the last position they are in phase, let's use orange, is actually alternate points at the rest position. So I got 1 point rest position, another point here, another point here, another point here, another point. Now what they say here is this: Q and T are in phase because these 2 are in rest position and they are alternate points from each other. That means Q, the next point is here. So I must skip this point, go to the next one. This is the alternate rest position. Okay, so that's why Q and T, they are in phase. Now, which are some other points that are in phase? So I'm going to use red color here. Okay, so I'm going to use this example of rest positions that are alternate. So if this is the point, I want to ask what other points are in phase. Okay, so what other points are in phase with this? So can you see this is a rest position? Another point that's in phase with this, okay, is an alternate one. So skip this over here. So skip the next one, jump over here. These 2 points are in phase. Can I find another rest point that's in phase? Yes. Skip this point, go to the next one. Okay, alternate rest positions. These 3 points are considered in phase. Now the question is, why is this term of in phase so important? It's because of this, the wavelength. So the wavelength of a wave is the shortest distance between any 2 points that are in phase. It's like, why so cheap? Okay, now this is the actual definition of a wavelength. But in simple terms, if I were to paraphrase it, it's actually the length of one complete wave. I mean, this is in terms of trying to understand it. The length of one complete wave is actually a wavelength. So how do you know it's a complete wave? Because the 2 points are in phase. Okay, any 2 points in phase, you know that that's one complete wave. Then if I measure the distance, I will get the wavelength. So now, because it's a distance here, the units is meters. So how to find the wavelength? Most of your teachers would have told you, okay, just take 2 successive crests. So from here to here, this is a wavelength. So this is lambda. Lambda is like a Chinese character called Ru. So this is a possible wavelength. This is another wavelength. Can you see? One crest to another crest, one crest to another crest, because we know that all crests along the wave are in phase. One wave, 2 wave. What's another possible way to measure wavelength? From here to here. This is a wavelength, because one trough to the next trough. You see the third one over here, any 2 nearest points are in phase. So Q and T, we know they are in phase. So from here to here, this whole point here is also lambda. So no one says that wavelength is only crest to crest. It could also be a trough to another trough, or it could be from one rest position to the next alternate rest position. That's also one wavelength. So there are different ways to look at wavelength in this kind of scenario. Okay, so this is wavelength. Now, this is, if you think about it, okay, how do we capture this? Is because when the wave is being formed, when the hand is moving up and down, the person took a snapshot, okay, the person took a picture of the wave, and this is like a still image. Okay, just imagine it's like a camera image, a photograph. So from the photograph, what actually can we get? Okay, we can actually convert it to what we call a graph. Okay, so this whole wave here is actually like this. Okay, so you can see PST. So the textbook tried to put it as clearly as possible to compare this image to the one at the bottom. Okay, so it's actually the photograph of the rope at an instant. Okay, it's equivalent to what we call a displacement distance graph. So it's called a displacement distance graph because the y-axis is the displacement, the x-axis is the distance. So it's a y to x-axis kind of graph. Okay, so what can we get from this graph? Why would you need to know about this graph? It's because from a displacement distance graph, I can get two things. One is the amplitude, two is the wavelength. So as mentioned here, you can see from one crest to another crest, if I know the distance, this is 10, this is 50. So if this is 50, this is 10, what do you think is the wavelength over here? It will be 40 cm. Simple. So because a graph has all these little measurements here, you are able to determine the length easily based on the graduations that's here. Next one, amplitude. So this is an amplitude. So if I were to look at it, okay, it's actually 5 cm because from 0 to 5. I can also take from here all the way down to here. So I say, sure, for this one here, the amplitude negative lecture down here negative 5. So for the displacement wise, we don't take the positive or negative, we just take it as what's the distance like this. So don't care whether up or down. From here to here, right, the distance just measured as it is also 5 cm. So from a displacement time graph, we can get the amplitude, we can get the wavelength. Okay, so why you use a displacement distance graph? It gives you a good visual in terms of the measurement of the lengths, so that you can determine the amplitude and the wavelength. Okay, next, we're gonna look at another type of graph called displacement time graph. Okay, so a displacement distance captures at a particular instance, so it's like a photograph of the rope. A displacement time graph is slightly different. What we are tracking is actually, what we are trying to show is the displacement of a point. Okay, this is a point on the rope. So we track the displacement of a point on the rope against time. So I want us to look at the first one. So imagine when you take a snapshot, Q is originally at the rest position. So I'll plot, okay, at time equals 0, Q is over here. At 0.25 seconds later, Q went up. So Q is at a crest. It's all the way at the top, 5 cm. So 5 cm displacement. This is the next position of Q. So this one over here. This one. So yeah. This one over here. Then the next one at 0.5, Q went back to the original position over here. So this third graph goes to here. 0.75, oh, Q went all the way down. So this is the next point. So this part goes to here. And then this one, Q goes back to the original rest position, goes to here. So you realize we have plotted 1, 2, 3, 4, 5. And how do I get this graph? Is actually by completing the dots, tracing the dots together, and you're going to get this nice graph over here. So this graph is actually taking the position of the particular point you're measuring with respect to time. Okay, so the question is, isn't the displacement distance graph enough already? Why do I need the displacement time graph? What can I get from it? So what can I get from a displacement time graph is actually the concept of amplitude again. At the top also can ma. So what's the difference between this compared to the displacement distance graph? Is that the second thing I could get that's unique to this is the period. So what exactly is the period? So this is where the next definition comes in. The period of a graph of the wave is the time taken to produce one complete wave. So can you see this red color is one complete wave? Because I track it along with time, I know that one complete wave takes 1 second. One complete wave takes 1 second. So I know after having a displacement time graph, I'm actually able to determine the period. So from a displacement time graph, I can get amplitude, I can get period, right? And because this is the time taken, the SI unit will be in seconds because it's the time. Now, once I'm able to get the period, I'm actually able to get one more thing. It is called the frequency. Now, what exactly is the frequency of a wave? It's actually the number of complete waves produced per second. So if I look at this question here, this is one complete wave that is produced in 1 second. So the frequency is 1. However, if in 1 second, it is time slash seconds. Let me draw a nice wave over here. So if you look at this here, in 1 second, now I got 2 waves. So what do you think is the frequency here? Because frequency is the number of complete waves produced per second. This will tell me that my frequency for this graph is 2 Hertz. 2.0 Hertz. Huh? Why is Hertz? Because frequency, yes, is a new term. Do take note, the units here given is Hertz. Hz, capital H. Now, the thing is this, what if they give us like that? Then what if they give us not so nice number? What if it's not 1.0, it's some sort of a weird number? What can I do? So there is a formula here to help you. So if you are able to find the period of a wave, you can actually find the frequency using F equals to 1 over T. F is the frequency. It will be in Hertz. Time here, T here is actually period. Okay, it's not time, it's period, capital T. The units is in seconds. So most people forget about the units. So the units are quite important here. For you to get Hertz, you must use seconds. And last 2 things here. Next, if I can get the frequency, I can get the wavelength, I can get all the things. Let's say assuming I got the wavelength from the first graph, I got the period in the second graph, I can actually find out how fast my wave is traveling. So the distance traveled by the wave per second is known as the wave speed, right? Meter per second over here. So the formula to tell you about the wave speed, there's 2 parts here. V equals to lambda over T, or I can use V equals F lambda. Most people are very familiar with this. Okay, but in actual fact, both are actually usable. Okay, both are actually usable. My suggestion is stick to this. Okay, because once you got a period, you can always find frequency, and from the frequency, you can always apply this. V equals to F lambda. Right, for those of you whose math always struggling, you cannot do the manipulation properly, or once you bring over, you're always confused, right? So if you need to use a triangle, this is the triangle for V equals to F lambda. Okay? Now, the last term that is introduced in wave is actually what we call wavefront. It is an imaginary line. Okay, it's not a real thing, it's an imaginary line that's drawn, okay, that joins all adjacent points that are in phase. What do I mean? So you look at this here, when there's this deeper thing going up and down, it actually produces many waves going from this side all the way to the other side. And if I were to take the first crest of this wave, take the first crest of the second wave, if I were to draw a line like this, so first crest, the second crest, I join them up together. The third crest, I join them up together. The fourth crest, I join them up together. So these 4 lines here are what we call the wave front, because they join all the adjacent points that are in phase. So the first crest to the next first crest, right? This is what they call the adjacent points that are in phase. So one wave front, one wave front, one wave front, one wave front. Now the question is, why do I need to know about wavefront? This has nothing to do with all the calculations I'm doing. So where is the importance in this is that from one wavefront to the next, this is actually lambda. You can find the wavelength from one wavefront to the next. This is another wavelength. This is another wavelength. Okay, so 3 wavelengths here because from one wavefront to the next. Circular ones also possible. So from here to here, this is one wavelength. Here to here is another wavelength. So these circular rings are also known as your wavefronts. So wavefront is not only straight lines like this, it could also be circular ones. Okay, so these are just examples of the calculation. My suggestion is look through the work example 11.1 because this will give you a rough consolidation of what the calculations you need to know and how to go about applying what you have picked up prior to this. Okay, 11.2 also a good example to look at, right? And actually, I think I've seen this in the O-level questions before. So this kind of diagram. Okay. So in actual fact, I think we are done. So let's do a wrap up for 11.2. Okay, let's do a wrap up for 11.2. Oops. Okay, let's do a wrap up for 11.2. So what we did was to find out that, okay, crests are the highest points, troughs are the lowest points. Okay, so we are using this crest and the troughs to indicate the positions of a wave. And why are they important? Because from one crest to another crest, we know it's a wavelength. One trough to another trough is a wavelength too. Okay, so we have picked up on this. Amplitude is the maximum displacement. SI unit is meters. Yes, we have done this. The wavelength is the shortest distance between any 2 points that are in phase. So what are the 2 points that are in phase? It can be from a crest to the next crest. It can be a trough to the next trough. Can be from a rest position to the next alternate rest position. Okay, so done this, done deal. Period. Time taken, we've really just gone through that. Time taken to produce one complete wave, SI unit seconds. Frequency is a lead up, okay, and how this is linked to, how's frequency linked to period? We got F equals to 1 over T. So what exactly is F? The frequency is the number of complete waves produced per second. Okay, per second. So if you're able to get the frequency of a wave, if you're able to get the wavelength of a wave, this two comes, this one will now come in handy. We are able to find the wave speed, how fast the wave is traveling. So because frequency can be found from the period, wavelength can be found from a displacement distance graph, I can actually take V equals to F lambda to find V. Okay? And lastly, we've gone through what exactly is a wavefront. Importance of this is because you can find lambda from wavefront. Okay? So I say again, you can find lambda from the wavefront images. Okay, and this is commonly tested also. Okay, so yes, I think that is about all. But there's actually something I need you to take back from this science bite over here. Okay, so listen carefully. What is this little thing I need to take back from this science bite? It's actually from point number 4. Okay? Now, shallow waters, wave decreases in speed. When we talk of shallower waters, it means most probably it's going from a deep waters or deeper waters. And so deep, let's go from, I want to highlight this point over here, from deeper waters, okay, to shallower waters. What actually happens is that the wave speed decreases. So slow down. So I say again, when we go from deeper waters to shallower waters, actually the wave speed, okay, decreases. It means that the wave actually slows down. Now, obviously, the other way is true. If a wave is traveling from shallower waters to deeper waters, it will actually speed up. This is an important point I need you to note because some of the questions do sometimes apply this. Okay, do sometimes apply this. So do take note of this. And I thought this idea of tsunami being mentioned here is quite interesting because now what they say here is that when the wave decreases in speed and wavelength, they actually increase in height. So it's not surprising why from afar when the waves are coming in from the earthquake, initially the waves don't look so high because they are in deepest water still. But as they come nearer and nearer to the shore, okay, what happens is that the water is getting shallower and shallower. So when it's getting shallower, actually this will actually cause an increase in the height, and therefore whenever tsunami reaches us, it's a very tall wave. Right? This is a little bit more of a understanding of how tsunamis are formed and etc. Okay, so that's all for this chapter.